So this is an example problem. This is what I mean by we're trying to solve a kinematics problem. We have a car that's 1,000 kilograms and it's traveling at 40 meters a second when it suddenly hits the brakes. Now the braking force that it provides is 8,500 newtons. We can figure that out from various ways. We can test the brakes effectively, but we'll say that's the minimum force it has, or the maximum force it has. So the question that we want is, how long does it take the car to stop and how far? So let's organize this first like a kinematics problem. All right, so everything's moving in the x direction. And so delta x is something we want. V initial is something that's given, is 40 meters a second. V final is 0. The acceleration we don't know, and the time we don't know. And if we organize the kinematics problem like this, we realize something's missing because we only have two numbers, and what we really want is one of these other ones to figure out what we need. So my suggestions when we get kinematics was try to find the time. But we don't have any other information. This is just something driving along a road. It's not falling. We don't have X and Y motion data so that we can find the time. So we're kind of a little stuck. If we didn't have one of these other things, then we need to find a different source of information. So this is our goal, is to find the acceleration. So that's why if we're told something about the forces involved, we probably want to try to find the acceleration. So one of the things we can do is draw a free body diagram and try to figure out what the net force is. So this is the important thing. We also have to put in some coordinates, x and y. And importantly, this 40 meters per second is in the x direction. Right? There is no y component. V0y is 0. So there's only velocity in the x direction. So that gives us a little bit of information of what's going on, is there's no acceleration up and down because it doesn't leave the road. That's what cars hopefully stay on the road. So we can make some assumptions in a problem like this. Right? We're obviously going to have a weight force because we're driving a car on Earth, and it's by the Earth on the car. We're going to have some support force, a normal force, by the road on the car. And then we're going to have our braking force. And this should be a little bit smaller than these because we can figure out what the weight force is. It's going to be this times g. Right, so that's going to be 9,800. So this should be just a little smaller. But this will be our braking force. And it could be from the brakes on the car. It could be the friction of the road on the car. I'm just going to say it's by the brakes on the car itself. But this is the thing that's 8,500 newtons. And we can see these things, these two are going to equal out. Right? But we've drawn our diagram, and the important bit is what we want is the acceleration in the x direction. And this stuff is all in the y direction. So we can ignore it. We can just focus on this. And so the net force in the x direction is this braking force. Now, this is the thing, is we know the size of it, but it's to the left, and we've taken rightward as positive, which should make sense. We're slowing down. We want a negative acceleration. And so this will be minus 8,500 newtons in the x direction. So now we can write the acceleration is sum of forces over the mass. And the sum of the forces is this 8,500 newtons. over 1,000 kilograms, and that is minus 8.5 meters per second squared. And now we can put that into this 8.5 minus meters per second squared, and now we can get everything else we need. Now we can get how long it takes to stop and how far. The time is our change in velocity over the acceleration, and so that's minus 40 meters per second over minus 8.5 meters per second squared. And then we grab a calculator, we wake it up. 40 divided by 8.5 is 4.7 seconds. Ran out of space. Got a little space right here I'm going to write. Our delta x is based on this stuff moving. I'm going to use the time that we just found. It's going to be 1/2 v final plus v initial times t. That is 1/2. We'll have 40 meters per second plus 0 times 4.7 seconds. And so we have 0.5 is 1/2 times 40 times 4.7, and that is 94 meters. All right, so the idea is that we're using forces in this sort of problem to get us information to solve the kinematics problem. All right, so you may not necessarily see that this is a forces problem, but if the acceleration's missing, then odds are that's how you need to attack it. You need to find forces. So, right, we're going to update. So I'm going to pause the video, and we'll switch to a new problem. And this one, I'm going to introduce a force. I'm going to start introducing types of forces. So I've already introduced normal force in a sense, but I kind of want to get to something that's in the Radford homework and a little bit in the Governor School homework, and we'll advance from there. All right. So what I want to introduce is tension, and so it's a property of things that are like strings, ropes, cables. You can imagine the ink pen that I have here. If I hold it on both ends and I pull, it has tension in it. It's a property of something that you're trying to stretch. You obviously can't see much in my hands, but tendons, and there we go. Tendons in your fingers and wrists and arms and such. Ligaments. If you try to pick someone up and they pull on your arm, your arm has tension in it. It's any sort of pulling force. That's I got to put that in as important. It is a pull. Any sort of pulling force that's along something that could stretch, like a rope or a cable or a ligament. And we're going to pretend that it's constant throughout an object. All right. So if we have one rope, then the tension in it is constant. Now, we could have two, right? We could have, say, the rubber band is going to count as one, and there's an object. All right, so we'll use an ink pen. And then we're going to have another, we'll have this one. These can, in principle, have, the yellow string and the rubber band can have different tensions. You can kind of, as the pen accelerates, there'll be different tensions. So we're going to try to solve a problem with tension in it. All right, we're going to use the same sorts of ideas. And this is also where we're going to use third law of forces and having multiple diagrams. Let's say that we have two blocks. There's 300 kilograms and 200 kilograms. And over here, someone applies 100 Newton force to pull it to the right. So we'll also put in that we have coordinates plus x and plus y. So we can ask, what is the tension in this middle rope connecting these two? All right, and that might be important, is if we have to tie these together like this, we don't want to exceed the tension strength of this rope, so we want to know what this is. And then we want to know how this accelerates. Right, so we have a couple of goals. We need to give this person a name. Let's say John. Right. Just so that we can label the forces on these appropriately. So what we're going to do is label these boxes. I want to call this one A and this one B, so that we have consistent, labeling. And now we're just going to draw in diagrams for these. This is the diagram for A. Right, and we're going to ask what forces are acting on this object. Well, there's a weight force. And unless you're not told you're not on Earth or not contacting some object, so we're pulling it along the floor. This is the Earth on A. And then there's a normal force, a support force, so it doesn't fall through the ground. And that is the floor on A. Now, we can ask what other forces are there? Okay. Well, you're obviously applying this 100 newtons of force to it, so let's put that in. This should be smaller, but I've goofed. That's okay. Maybe these things are scaled, like maybe it's like that. So this is going to be our 100 newtons of force. I'm going to call it an applied force by John on the block A. So we'll call this our applied force. And is this right? No, it's not right. Because John isn't touching the block. He's touching the rope. This is a tension force by the rope on block A. That's the correct labeling of this. So we may have to distinguish this as by the right rope on A. As in, we got to put, there's another rope and it applies tension. And there it is. It is the tension by the left rope on A. But now we can draw the diagram for B. I'll draw it over here. Now these weight and normal forces should be a little bit larger because it's a bigger block. But they should be there. And then this rope has to be pulling the block. So there has to be a tension. And this is the tension by the left rope on B. All right. So I'm going to ask y'all here. So I'm going to pause for just a second. Is there third law forces here? Okay. So if anyone said that it's the tensions, well, we should consider our criteria for third law forces. All right, this is our third law. It's, oops, wrong diagram. Sorry about that. Here it is. This is our criteria for third law forces. It is a force on different objects, and it's an interaction between the two objects. All right. That's the thing, is this rope is one of the objects. We could put a free diagram body for each rope. So we have things that are on different objects, yeah. And we have things that are equal in size and in opposite directions. Yeah, these are equal. Tensions are equal along the length of the rope. But these are all forces caused by the rope itself on different objects. There's 3 objects involved here. For this, if we had a force by 2 on 1, the third law pair is by 1 on 2. It interchanges these labels. All right, so you can only have 2 objects. Tension forces usually are not third law forces. So there isn't any. But these are equal because the tension is always equal along the rope. So with this diagram, now we can figure out our net forces. All right, and so we're going to ignore the y direction forces for the moment. We know they're equal because we know the blocks are dragging to the left. So this is for block A, the sum of forces in the x direction, x, not y, x, is our tension in the right rope on A. That is in the positive direction, and in the other direction is the tension in the left rope on A. And what we're doing, there's a minus sign here because they're in different directions, but we're adding these two. We're doing a vector addition of these. So it'll look like this plus that. That's what it's going to look like. And so the sum is going to be that little bit there. And then on B, we have the sum of forces in the x direction is just the tension in the left rope on B. So we have an idea of what some of these numbers are. Here, the sum of the forces in the x direction is, well, the tension in the right rope is 100 newtons. That's how much we're pulling on it with. And that is going to be minus the tension in the left rope. And then this is just going to be equals minus the tension in the left rope. So we're going to write this on a new sheet of paper. So just hang on a second. Okay, so this is the stuff I'm trying to write from here. So we're still doing these free body diagrams, but this is our statement of adding up all the forces. Now, we need to figure out what this tension is in principle. And one of the things we can do is say, hey, sum of the forces should look like the mass times the acceleration of the objects. So this is going to be the mass times the acceleration of block B, and this is going to be the mass times the acceleration of block A. So we can take this and plug in this statement. And so we have 100 newtons minus the mass of the acceleration. The mass times the acceleration of A is the mass, sorry, this is B, and I've scribbled this up. Let me start again. 100 newtons minus the mass times the acceleration of B equals the mass times the acceleration of A. I should be careful. These are the masses of B and the accelerations. All right. So now we can move this over. And we'll have 100 newtons equals mass A plus mass B times the acceleration. Because, well, these things are physically joined together. The acceleration of A is the acceleration of B. So the things are joined together. There's just one acceleration. Right? That's kind of a subtle thing, is if these things were not connected, they could have different accelerations, but they're physically stuck together. So that means we can go through and say, hey, well, this is 300 kilograms plus 200 kilograms times A. So we can solve for A. This is going to be 100 newtons divided by 500 kilograms is A, and that is 0.2 meters per second squared. Hey, that's our acceleration. Yay. Now we can solve problems. But we can also go back up here and find the tension that we were looking for, right? So that was part of our problem, is we have the tension and the acceleration. So for the tension, well, this is an easy thing we can do. We can go yoink and say the tension in the left rope must be, well, this is for object B. So it's going to be mass of B times the acceleration of B. And that is 300 kilograms times 0.2 meters per second squared. And that is 60 newtons. And that kind of makes some sense to us, right? Is in our picture, this one rope on the right has to do all of the work to move the blocks. But this one only really has to move one block. It's just being drug along by the other one. Right? This one's not responsible for the 200 kilograms moving. It's just responsible for this one. So this tension being 60 newtons, that makes sense. What we can do is check with this, right? Is we have, let's rearrange this. The tension in the left rope is 100 newtons minus mass of A times acceleration of A. It has 100 newtons minus 200 kilograms times 0.2 meters per second squared. This thing is 100 newtons minus 40 newtons, and that equals 60 newtons. And so we know that's good. So yeah, if y'all are doing problems like this, right, I'm not expecting you to draw every little detail out, but at a bare minimum, you need to have the free body diagram, and you should probably have a minimal sketch of what's going on. You should have some statement that is the sum of all the forces in the direction you're trying to solve for stuff for. And then you should have your work where you solve it out. And I'm doing a lot of detail and a lot of extra stuff. You can skip some of these steps, but you want to be careful of that. All right, so there we go. So, yeah, this has been a long enough video as it is. We're going to do another problem, obviously, but we're going to pause this. We're going to stop this video. You'll see a third problem, and we'll call it there.